Hello and welcome to today's presentations on IP protocols. Basically, today I am going to talk about the Internet Protocol. The basic purpose of my talk will be to specify the various fields of the header formats of the IP protocol. But before we proceed further, let me show you the positioning of the IP protocol in the protocol stack. Let me show you on the top. You know that this is the applications layer protocols here, and there are series of applications layer protocols are there. We have a FTP, we have a Telnet, we have a DNS, we have SNMP and so on. So the series of protocols are sitting on the top of it. I'm just trying to show you the positioning of the IP protocol. And then comes the transport layer. Here we have again number of protocols. One is called TCP protocol, then we have the UDP protocol. There are many other protocols are there, but these two are primary protocols. Then comes the network layer. And here is sitting your IP protocol. But IP protocol does not work alone. It also takes the help of some other protocol, and these protocols are IGMP, ICMP, ERP. So these are the protocols, RARP. But the main protocol is the IP, and it's known as Internet Protocol. And again, below this one, we are talking about the data link layer, or we have a physical layer. So here is basically underlying LAN and WAN technology. So this is basically, and simply I will write technology. So now basically our discussion is confined to only this layer, and primarily I will be talking about the IP protocol. Now IP has again been in IP, the packet is called a datagram packet. The network layer, so basically this is a datagram. Now the basic unit of data transfer at the IP layer is called datagram. Now datagram contains two parts. One is the header part, and the second is the data part itself. So our discussions will be confined to the IP, and primarily it will be related to the header parts of it. Now, but before we proceed further, again let me just talk about some of the basic characteristics of the IP protocol. So to understand what the IP protocol is. One is that basically it is a connectionless protocol. It's a connectionless protocol, and also is an unreliable protocol. Now in this case, so basically it assumes that what you have is the underlying technology is very unreliable, and if you want to have very reliable transmissions at the network layer, then IP basically ties up with the top layer protocol called TCP. So you see, unreliable and connectionless datagram protocol. The another important feature of this one is the what we call them what will sometimes we say that the best effort delivery. It means that the IP provides no error checking and no tracking of the datagram itself. So these are the few important things about the IP datagram. Now let me just talk about some of the fields. The IP datagram consists of two basic fields. One is the header, which the size of the header is the minimum 20 bytes and the maximum is 60 bytes. This is the header size. So when you send email, again the email might be part of your data, but when you send email, again some attachment goes where this packet is going to, where from the packet is coming from. So all these things are part of the header. So the header part of your datagram contains 20 bytes minimum and maximum 60 bytes. And then you have the data bytes. Now here the data bytes, so total size of this one, the total size of the IP datagram will be maximum, so 20 bytes might go to 65536. So this is the maximum size of datagram you are able to send now. Now let me talk about each of these. So what the header format contains? So header has a large number of fields, and I will talk about before, I will not draw the basic diagram to show the complete fields at one go. Let me talk about each one individually. And the first one, the first field of the header. So header has many fields. So first field of header is what we'll call the version. Now IP is moving through some transitions. The current version of IP is of 32 bit, and the again in moving towards the 128 bit. So now this version, so the current version of IP is version 4, and we are moving to version 6. So the version field, this is a 4-bit field. The size of this version is specified into 4 bits. So this 4-bit field defines which versions the protocol belongs to, and accordingly the processing has to be taken by the remaining modules. IP is a very complex package. It contains number of modules, which we'll discuss in the next part of my discussion. So it contains number of modules, for example, reassembly module, forwarding module, so on. So now, so accordingly, if the datagram size is according to IP version 6, then it has to be processed accordingly. If IP version belongs to version 4, then processing has to be done differently. So the IP version that is specified in 4 bits will be able to specify that which versions this protocol belongs to. So this and the size will be specified into 4 bits. The second one that is very much important, and we'll try to solve few numerical problems based on this field. And the second field is again of size is 4 bits, and this is called as H lane, the header length. This one, what should be the header length? So this header length is defined through 4 bits, and by default, so basically minimum size is 20 and the maximum size is 60. So now this header is defined into bits now. So here is again which is defined into 4 byte words. It is needed because the length. So why we need? Because it has to specify that what should be the size. Sometimes you want to know what will be the size of data, for example. Then you have to know what is the size of your header, and that you have to specify through 4 bits again. So now so by default, the value of H lane is 5, which can be specified as a 101. This is what basically what we are talking about. By default, it is specified as a 5, and in binary it is 0101. And then again, if you multiply by 4, then it becomes 20 bytes. The maximum value of H lane will be 15, and then if you multiply it by 4, then it becomes 60. So basically the range of this one varies from the 20 bytes to 60 bytes. If the header length comes less than 20 bytes, then the modules, the forwarding, the processing module and the rest of the modules will not able to process and simply discard this one. It will assume, since the size is not of 20 bytes or less than 20 bytes, then system will assume that the whole fragment, whole datagram has been corrupted. So this is what we have. Now let's go to the another type of service. See, the third, this is first field, version field, H lane field, and the third is called service field. Sometimes now it is known as a differentiated service called DS in form. Now this is the format of the DS. The third field I am talking about, the number of fields are there. The first field is this one, the second field comes to the H lane, then the third field is of the service field. The service field, the format of the service field is like this. The first 3 bits specify the precedence, basically priority. What will be the priority of a datagram in case of a congestions? You know that if there is congestions in the network and datagram is moving, how the router will interpret it, whether packet has to be discarded or packet has to be sent on the top priority. So these 3 fields will define the priority of this packet. What has to be done in case there is a congestions in the network. And then there are some other fields are there, D field, there is a T field, there is a R field, and there is a C field, and so on. And the other few bits are left to be non-used. Now let me just talk about each one in detail now. So now already we have discussed the version, we have discussed the header length. Now what we have is in this case, let's just talk about what D stands for. D stands for minimize delay. means the packet, if packet is moving, each router has to minimize the delay in forwarding this packet, because the packet moves from one router to another router. So by seeing this field, the router will act accordingly, will try to minimize the delay in forwarding the packet from itself to the next router. Then T stands for maximize throughput. So this way, these are the various parameters are available to specify the services you want from the IP layer. The maximize throughput basically means if the router is able to process or send 200 packets per second, for example, and some router is able to send 400 packets, so throughput is much more higher for the second one compared to the first one. So the throughput, how many more packets you can send, it means the router has to send many more packets. The R stands for maximize reliability. The reliability is much more important. Throughput might not be issue, the delay is not a criteria, but the reliability is more important. So in this case, R field has to be addressed, and the fourth field is called minimize cost. So all these parameters are available, and according to the needs, the parameters value are set or reset. So for example, if this value, if the four fields, if I write 0, 0, 0, 0, if all fours are 0, it's normal treatment, no other priority, no other specific way to handle these packets. It is a normal way the packet will move from one router to the another router. But when we have a 0, 0, 0, 1, then it will be, means this field, particular field is set to be bit 1, then it means that the C is set to 1 and other remainings are 0, and what is C is minimize cost. Sorry, this is cost. So now the router will try to minimize the cost for forwarding the packet. If we have a second one, let's see, if 0, 0, 1, 0, then we are talking about reliability issues. If we have 0, 1, these two zeros, then we are talking about the throughput has to be increased. And then finally, if 1, 0, 0, 0, then it means the delay has to be minimized. So accordingly, the value will be set to 1 or 0. This is one, the third field. Let's have more further discussions on the header fields. The next field is what we call them total length. By total length means this one plus this one, and this is specified into 16 bits. So 2 to power 16, it basically is very, very high. It comes to 64K, because 2 to power 10 is your 1K, and then multiplied by 6 to 64. So total is 64K. So much size of the datagram can be sent. Right now, the IP, the next version might give you more the size, bigger size than what IPv4 is supporting now. So this is basically specifying that what will be the size, what is the size of a datagram. So this is this one now. So for example, the total, you know that the total length is header plus data. So if you know one of this one, you will be able to retrieve the second one. Let's say try to, with whatever we have discussed, let me give one small example so that you understand how basically we'll try to understand all these in the real practice now. Sometimes the questions we ask or whenever you see the manual or the book, this is very important questions we always ask, and that is why we are discussing, we have asked in the term and paper also. Question is, why we need this field, that is the total length field? Because many times the router drops the header and the trailer leaving the datagram. So basically the router drops this field, I mean the header fields are getting dropped, or the trailer field of the datagram gets dropped, and so on. So why we require a total? Because router finally drops this header field or the total field, whereas total lengths specify the total size, where the router drops some of the fields while forwarding the packet from one to this one. See, the answer to this question is that many cases, in fact, we don't need this such field, but there are situations where we require to have presence of this type of field. Look at the Ethernet. You know, Ethernet is basically MAC layer protocols. and most of our system, the LAN, we have Ethernet protocol is running now. Now look at the Ethernet frame. This is basically what Ethernet does is, Ethernet does is like this. Let me just show you the Ethernet frame. The question we are trying to address is why we require this field if a router many times drops the header of a datagram and the trailer of a datagram. Why we require all the time? But so most of the cases, yes, we don't require it, but there are certain situations which I am trying to give an example of it. We require it. Let's take example of Ethernet protocol. Now what Ethernet says, Ethernet frame is like this. It has a header, it has a trailer, and in between it has a data field. And so if data field is less than 46 bytes, then it does some padding. So what it does is that if data field is less than 46 bytes, it does add some values to it, add some 0000. So in this case, in this situation, so one has to know what exactly the size of the data, what is exactly the size of the padding and so on. We require this type of field, and that is very much important to understand what exactly, how much data this datagram is carrying on. Now let's go to, there are many other fields called identifications field. There is a field called flags, and we have a fragmentation offset. The fragmentation offset will come in different contexts, but they all are related to the fragments. Sometimes the size of datagram is too huge, which Ethernet might not handle them or router might not handle them. In this case, they try to break this whole datagram into number of fragments, and at the end they try to reassemble them. So in this case, one has to keep track of that which fragment which belongs to which datagram. So identification field is able to identify, basically used to identify the particular which fragment belongs to which type of datagram. It might happen depending upon the size a router can handle at a time, and depending upon the size of a datagram a router can handle. It can have many fragments, or it might not have more than one fragment. So now if you have many fragments, but they all belong to same datagram, you must be able to identify which fragment belongs to which datagram. There might be many fragments as well as many datagrams moving from the source to the destination through several series of routers now. And now finally it has to be reassembled at the destination. Now destination must be aware of if this fragment belongs to datagram 1, this fragment belongs to datagram number 2, and so on and so forth. And so identifications field is basically used for that purpose. So each fragment must have some ID, each datagram must have some ID, and they are all able to relate to each other. Then I will look at some of the program on this one, so you can understand this topic very well. Let me talk about another field called, sometimes called TTL, time to live. How long the packet will live, means basically they move from one packet, one router to the second router to the third router and fourth router and so on. So the time to live basically used to control the movement of a datagram in the net or subnet. So how long? So basically by this field, system is able to calculate how long this packet will survive in the net or in the subnet. The next field is what is called protocol. It basically specifies the protocol. I am not writing how many bits it requires because the standard textbook talks about everything. Here is simply explaining various concepts. So the 8-bit field defines the higher level protocol that uses the services of the IP layer. I have shown you the positioning of the IP layer in the beginning. I have shown because IP lying at the network layer, that on the top we have a TCP, on the top on the above of TCP we have a series of, we have a large number of applications layer protocols. So now IP layer is basically this protocol with this 8-bit field specifies that which higher layer protocols wants to take services of the IP layer. So now and again there are different bit sequence are there for particular type of protocols, either TCP or UDP or some other higher layer protocols now. Now let's say this is all. Let me just see again, we have covered 3, 4, 5, 6 fields. Let me just take one small example to understand how these fields are basically used. Let's say for example, packet is moving from one router to the second router. Now this router, the second router, after receiving a packet, discards it. Let's just see what this packet is. So the IP frame, IP packet has arrived with first 8 bits, which is shown as below: 0, 1, 0, 0, 0, 0, 1, 0. Now this is what, so there are a series of, because 32 bits, I mean this is basically shows into 32 bit sections. Now what I am trying to explain to you is that, let's say this is the IP datagram, just I have shown only 8 bits. Now IP data shown 8 bits, the router which receives this one discards this one, means that this packet seems to be corrupted. Now the question is how to understand that when the packet will be corrupted, how the, I mean when the router is going to discard the packet, or when the router is going to accept this packet. What is wrong with this one? Although I have just shown only 8 bits. What I have shown is, now let's try to interpret. This is a datagram. It always goes into the bit sequence now. In IP header, what we have discussed in the beginning, the first 4 fields defines the version, which version it belongs to. Now this is 4. This is in binary, this is 4, it means IPv4, means this is correct. Either it can be an IPv4 or it can be IPv6. So now it is already 4, it means that this is correct, and the remaining, the modules of the IP package will process according to the version 4 and so on. Now what this is, what is the next 4 bits? The next 4 bit we have discussed, it is a header length. So I am writing header length. So first bit is version, this is 4 bits, this is correct, nothing wrong here. But there seems to be some problem here. That is why the router is not able to accept this datagram. It is basically discarding it. Sometimes to send the packet gets bounced, or packet does not reach to the destinations. Right? So it might be a problem here. What is the problem here? Is that this is, it is in binary, it is equivalent to 2. If 2 means 2 multiplied by 4 means 8 bytes. So it is a header length. Now what we have discussed in the beginning, the header length must be minimum 20 bytes. To become a 20 byte, the minimum value of this field should be 5. So instead of this one, it should have something like this. It should be have 0. If this is the case, then it is correct. But now it has been corrupted. It has been corrupted. Now 1 has become 0. This 0 has become 1, and this 1 has become 0. It should have been 1, 0, 1. But there is a corruption because it has been corrupted, and due to this one, the bits have changed its value from 0 to 1 and 1 to 0, and from 5 it has become 2, and 2 will be multiplied by 4. It just remains only 8 bytes, and its minimum should be 20 bytes. Unless the 20 bytes header length is there in the datagram, the packet is not going to accept. Is less than, it is not going to accept it, simply it will discard, and packet has to be resent. So this way you try to understand what is exact meaning of the header length, what is the meaning of the version. Let me just again, question number, so we exercise 1, let's exercise 2. This next exercise which we will do is like this. In an IP packet, the value of h-len, that is this one, is 100. Now the next question, here the value of this was just 2. Now I am taking 0010. Now in the next questions, the value of h-len is this one, 1000. What is 1000? It is equivalent to 8. This is the question. So the value is 100, that is 8. Okay, how many bytes of option are being considered by this packets? So there is a, if you look at the IP header format, then we have the last portion of it, our last section of the IP is left for an option. Now the question is, if an IP packet, the value of h-len is 1000, is in binary, I will not call them 1000, is 1000, how many bytes of option are being carried by this packet? Now what we have is, now what exactly we have here? See, in this case, the HLN value is 8, which means the total number of bytes it is carrying is 8 multiplied by 4, that is 32. The first 20 bytes is the header file. In this case, if it exceeds 20, then first 20 bytes, that is minimum requirement of header length, is for the what we will call them the H lane will be, in this case H lane will be 20 bytes, and remaining 12 bytes will be left for the option field. So 32 minus 20, it becomes 12, and that is basically for the option. Now let me just question again, refine the question. What we have question was that if this is the field, if the value of HLN field, how many bytes are left for the option field? Because if you look at the IP diagram, IP header format diagram, the few sections are for the actual HLN, and the remaining, the last one is left for the options now. So if this is the value, what is the actual HLN value, and what is the value of the option field? So 8 multiplied by 4, that becomes 32. Actual HLN is just 20. 32 minus 20, the remaining 12 bytes are for this one. This is so. Let me just do one more exercise so that you understand the exercise 4. What we have is, let's say in IP packet, now we are moving from binary to hexadecimal system. You know that in computers we use binary, we have an octal, we have a hexadecimal system. Octal requires only 3 bits to represent, and the range is from 0 to 7. In hexadecimal we have a 16 number, we use from 16 digits from 0 to 9, then 10, 11, 12, 13, 14, 15, 10 is represented as A, 11 is represented as B, and so on. So now the question is, now here the exercise 4, the value of HLN is 5. Now 5 is defined into hexadecimal format. This is where the base is, or radix is 16. And the value of total length, this is my total length. What exactly total length? Total length is header plus the data. And what is the minimum size? What is the size of the total size? I mean, how many bits we require? 16 bits now. So the question is, the value of HLN is 5, 16, base 16, and the value of total length is TL, total length is 000028, again in hexadecimal format. Now the question is, how many bytes of data are being carried by this packet? While defining the total field, we have given you the idea that it basically defines what is the total size of your datagram, which comprises 2 fields, the header field as well as the data field. Now in this case, the total field is given, total length is given of a datagram is this one, and this value is given, remaining you have to find out. But it has to be calculated into the hexadecimal format. Let's try to do this one now. So the HLN is 5, means again again it is 5 itself. So 5 multiplied by 4, again 20 bytes. 20 bytes is my header field. Now 20 bytes is header field, and then what about the number of, what about the total length? Total length will be, if you try to calculate into the hexadecimal, it becomes 40, because 16 multiplied by 2 plus 8, 32 plus 8 is 40 bytes. So now, so 40 bytes is your total length. The header format is, header field is 20. You just deduct this 20 from 40. What you are getting is the data bytes. So what we have calculated now, given the header length, given the total length, you can calculate what is the size of the data bytes. This is what we are trying to calculate now. So we have considered various options given this in the binary sequence. You can easily say that it is a correct header field or a wrong header field, and so on. Now let's move to the let's do some more the rigorous exercise of different kind. Let's try to increase the fragment, the datagram. Let's say a particular router has received of this kind. My question is, the next exercise which we are trying to do, a IP packet has arrived, or IP datagram has arrived. with the first few hexadecimal digits as shown below. Now this is hexadecimal 4. So a router, one router or the sender, the source machine has sent some data. It goes into the IP datagram, and few bytes or few sequences of bytes or digits has arrived in this format: 45000000. Then we have 28301. Again we have a 1230, then 102. Now this is the again IP datagram. Earlier I have taken only in format of binary. Now to optimize it further, to make it much more compact, we have taken them into the hexadecimal format. Each one is hexadecimal, and each hexadecimal digit requires 4 binary digits now. Now the question is, the question we have now, so I have sent from this packet, this machine to this machine has received this one. Now the question is, how many hops can this packet travel? This time to live is somehow related to time to live field. The question is, I can generate many questions out of this one now. So for example, I can ask, what is the header field here? Where is the header field? Where is the version field? The first one is version field. The second one is this one, is correct because it's 5. 5 multiplied by 4 is 20 bytes. This is IP version 4 and so on. So this way, if I know the field size of each field, if I know the size of each field of IP datagram, I can simply read this one. I can find out where is what field is located in hexadecimal form. So now the question is, how many hops or what is the time to live value in this sequence of hexadecimal digits? So this is my question. How many hops can this packet travel before being dropped? The data. Okay. So now solution. So what will be the solutions now? Now what we have to do to find out time to live field, where you can easily read from, by reading time to live field, you can specify how many hops it can travel. So you have to find that you have to skip 8 bytes. 8 bytes means 16 hexadecimal digit you have to skip. So this is my first hexadecimal, this is second hexadecimal, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is my 16. So it says that what is the value here? Value here is just 101. Now in this case, what we can say that time to live field here is the 9th byte, which is 01 means 1. It means that packet will travel at most 1 hop. Because the value is 1 means at most 1 hop it will travel, means it can maximum send from one router to another router, and after that it will be discarded because already time will be expired. So this is basically meaning. So once you are given, the purpose of discussing this header format of IP is that given this type of sequence, you can easily find out whether the datagram format is correct or not, whether it has been corrupted or not, and you can interpret the various field in terms of which version it belongs to, how many hops it can travel, what type of services it is a top layer wants to take from the IP layer, how many hops it can travel, and so on. So this way one can do now. The another important component of the IP is what we'll call them. Let me just try to understand one of the important component is somehow what we'll call them the checksum. The checksum in IP datagram. It basically checks whether the IP datagram is correct or not. Now what we have is, in this case, is let me just explain now what exactly is. What is the process of checksum in IP? There is one field which is reserved for it. Initially it is set to 0, and then checksum is calculated based on certain method, and then checksum value is inserted into it, and finally it's sent to the next destination. So the process of checksum in IP is as follows. The value of checksum in the IP header format is set to 0. Then the entire header is divided into 16-bit sections. So we have IP header formats, and we take one section as a 16-bit. For example, for example, you can take like this 4 bits. 4 bit is basically reserved for the version field, 4 bit is reserved for the header length field, then 8 bit is reserved for, let's say, some other field. So we'll combine 16 bit and make them as a one sections. There are many fields are there, therefore you will have a many sections there. So value, so the value of checksum field is first initially set to 0. Then the entire header is divided into 16 bit sections and added together. First section, second section, third section, fourth section, we'll add them together. Then result will complement, will take one's complement of the result field, and finally whatever we will get, we'll put them into the checksum. So let's say it's something like this, graphically, which I can represent like this. This is my sender and this is my receiver. This is my source machine, this is the destination machines. Destination might be somewhere else in some other country. What destination machine? It is some machine, this type of machine which is connected to some router. We assume that we all are part of the internet. I have internet connection. The receiver is also connected to the internet. I am sending some packets. This happens inside. You as a user simply send email or do FTP or whatever you want to do. But inside the system, this type of process goes into it. It's a background process. You as a user simply know the particular type of package through which you can send your email, or you can do FTP, or you can browse your internet. But inside, finally, this type of process background keeps on running. And purpose is that you understand what happens inside the system. So we have a sender machines. Now sender will have, again, they will send the packet into the IP datagram. IP datagram have header field, data field, and so on. Now we are trying to break the IP datagram in terms of sections, or let's IP header into series of sections now. The first sections, section 1, then again n bits, that is n bits is 16 bits, section 2, again n bits, section 3, again n bits, so on and so forth. I will keep on. My checksum section or checksum field again will be set to 0, and again I have next section, section K, again it will be n bits. I will add sum will be these bits, these bits, these bits, and finally I will get some value of n bits. I will take one's complements of the sum, and again from this one n I will get n bits, but this n bits will be different from this n bits because this is n complemented. So I will just simply write nc bit, right? So whatever value I will get, I will insert them here. So my checksum will be n bit checksum. The checksum value also will be n bit. Let me explain now what exactly task which we are trying to do. When we send a packet, we must send some value called checksum value, whether it is correct packet or going or not. So initially this value is 0, and then we do some process in which we try to have number of sections, and each section size will be of 16 bit, and then we'll keep on adding them, all the sections of n bits each. After summing, I will get n bits value. I will try to do one's complement of n bits. I will get another n bits. I will name them as nc bit, and then whatever value we get, we try to insert them into the checksum here. Now this will go. Here is my internet is here. It will reach to my receiver somewhere in other country, for example. This is receiver. There also machine will do similar exercise. Section 1 n bits, sections 2 again n bits, then checksum value which it has got here, checksum value which it got from here, n bits, again next section, again n bits. It will try to take sum of it, again it will get n bits, take one's complement of this sum, will get some value. It must get 0. If the one's complement of the sum is not 0, it means that packet has been corrupted. There is some noise in the packet, something has happened in the system. If it is 0, it means everything is okay. If it is not 0, it means something somewhere, something has happened. 0 might have become 1, 1 might have become 0. So checksum is important. Whenever you will send a character, the one field works as a checksum value. You say odd parity or the even parity. So parity bit is just like a checksum. But here is very value of this one is not 1 byte, it is a large number of bytes are there. So this is one of the important component of this one now. Then we have another important field called fragments. Again, the fragments are basically, you know that this is the last field of my IP. This is simply, I will show the format of this one, of my fragment. I told you that the size of this one, the datagram, again is broken depending upon the maximum it can carry over by the Ethernet machines or whatever be. It might have many large number of fragments might have been created, but there must be some way to identify all these fragments belonging to particular type of datagram or not. So this is way we have to. So now basically the field which they have is what we call them. One field is called D, one is called E, M field. D stands for do not fragment, the M stands for more fragments. So according to the value which is given here, it can have more fragments or it can have a less fragments and so on. The size of the fragment is 13 bits maximum one can have. So this way one can easily calculate all those value of this one now. Now what we have do, let me just summarize very quickly what exactly we have discussed now here, so that you can easily summarize very quickly what we have discussed here as part of my discussion series. But let me summarize very quickly so that we have first given you that IP datagram is a very unreliable and connectionless protocol. If it has to provide reliability, it has to tie up with the what we call them TCP protocols. The packets in IP layer are what we call them datagrams. The datagram consists of a header which varies from 20 to 60 bytes, and then it has a data. It has many important fields which we have listed: versions number, we have a header link, we have a services datagram link, identifications number, and so on. Checksum field, source address, destination address, and everything is defined. Source address is defined into 32-bit. That is why we say IPv4 is 32-bit. The maximum length of datagram, which includes all header plus data, is 335 bytes. Then we define what is the fragmentations. Fragmentation is the division of a datagram into a smaller units to accommodate the MTU of data link layer. And this way we have IP datagram consists of 20 byte section and variable option section with a maximum of 40 bytes. So this is the 20 bytes we have header, and remaining 40 bytes will go as this one now. Then we have the error detections method which we use in IP is called the checksum methods. What checksum does is uses one's complements arithmetic to add equal size section of the IP header. The complemented result is again stored in the checksum field. The receiver also uses one's complement field and also checks if it is 0. Same process is done both at the source side as well as the destination side. If it is 0 at the receiver side, it means the packet has not been corrupted and it gets accepted, and so on. This is all we had. We defined complete the IP. We try to solve few problems, and the exercise which you have to do is that you define the random byte sequence and try to figure out whether the packet is corrupted or not, how many hops it can travel, which version it belongs to, how to calculate the header field, how to calculate the data field, and so on. Thank you very much.